In this video, we are going to solve the energy balance combined with the entropy balance for 4 different constraints, and we are going to derive 4 different fundamental energies of the thermodynamics. Our first system is going to be a very familiar constant volume adiabatic piston and cylinder arrangement. And then the second system will be a constant pressure and adiabatic piston and cylinder assembly. The third and fourth will reveal themselves as we progress in the recording. So let's get started with our piston and cylinder assembly. Now, this is our piston and cylinder assembly. We're going to impose a constant volume constraint on it. We are going to secure the piston so that it cannot move neither up nor down. And this piston and cylinder assembly is thermally isolated from the environment. As such, there is no heat exchange. And of course, because the piston is secured in place, we have no volume change. dV over dt is also 0. Now what we are going to do is we are going to place an impeller in this piston and cylinder assembly. We have the capacity to introduce shaft work into the system. And we are going to check what this shaft work induces into the system. And our system is the gas confined in the cylinder. Now let's look at the first law. The pdV over dt term is 0. Q is 0. This is a closed system that these terms are 0, such that the energy balance reduces to du over dt to be equal to shaft work. All right? Now we have set the constraint of constant volume. All right? But let us finish this problem by looking at the entropy balance. And let's see where the adiabatic condition is going to lead us. Of course, I didn't stress it in the beginning of the problem, but we are going to solve for all practical purposes that this process is going to be reversible. Because this process is reversible, the entropy generation is going to be 0. The system is closed, no mass exchange is, no mass is coming in or going out, so these two terms are 0. Q over T, Q is 0, Q over T term as a result is 0, and as such, we have ds over dt to be 0 as well. Now, from the first law, from the energy balance, we observed that the shaft work is equal to the change in the internal energy, and from here we deduce that the entropy is constant. So in this system, volume is constant and entropy is constant. This is our first problem domain. Now let's solve the same problem for a constant pressure condition. We have the same piston and cylinder assembly, but this time we relieved the latches that secure the piston. Our piston is now free to move, but still our system is thermally insulated. There is no heat exchange, but P is constant. Now that we have derived here the entropy balance, the same conditions prevail. Process is adiabatic, reversible, and closed. As a result, this ds over dt to be equal to 0 also prevails here. And this is a constant pressure, constant entropy domain. Again, we have the impeller introducing the shaft work into the system. And our first law reduces to du over dt is equal to shaft work. But this time, my piston can move. I have pdv over dt term. As a result, my energy balance has one more term than the previous example. So I will reorganize this by putting P in the derivative sign. Because pressure is constant, I can easily do that. So my energy balance becomes du over dt plus dpv over dt. One more step in this calculation is du plus pv. Let me write here d over dt u plus pv, which is h. Or in summary, under these constraints, under constant pressure, constant entropy constraints, the shaft work that is done by or on the system, we really did not make any distinction, is equal to the enthalpy change. So this is the second constraint. The first constraint was to keep the process at constant volume and entropy. The second constraint was to keep the system at constant pressure and entropy. Now we are going to come to the third constraint. The third constraint is to allow the system to exchange heat, but don't allow the piston to move. All right, our system is going to exchange heat with the environment so that we are going to have a constant temperature and a constant volume process. Again, we have an impeller and we have a shaft work exchange with the environment. The constant temperature condition is going to be reflected back to our analysis as an entropy term in our equations. All right. We have du over dt term. All right. I did not say anything about the gas. I did not say that this is an ideal gas. It might be a real gas. And as a result, constant temperature does not immediately eliminate the u term. So I'm going to maintain the u term. Of course, now we all understand that this is a closed system. The first two terms, both in the energy balance and in the entropy balance, are eliminated. We have Q term. We have heat exchange. We have no shaft work. We have no P dV over dt term. We have shaft work. Now we are going to bring this Q from the entropy balance, ds over dt Let me divide the board so that we don't confuse the domains. ds over dt is equal to q over t. From here, q is equal to t ds over dt. And I will substitute this, and I will do the algebra as I did here. So I'm going to take this temperature into the derivative because temperature is constant. It really mathematically doesn't make any difference whether it sits outside or inside this derivative term. And I will take this to the other side of the equation to find out what my shaft work will be. Now the summation of u plus u minus ts, all right, u minus ts is called the Helmholtz free energy. I will write here Helmholtz free energy, all right? And why the energy is free, we will discuss later on, is equal to shaft work. Or, one more step, shaft work, this doesn't have a dot, we have integrated over time, so here I found a mistake. Shaft work is equal to delta A. You see, I set different constraints, and my shaft work takes different forms. My last constraint in this problem is going to be the same piston and cylinder arrangement, but this time, again, piston has the freedom to move up and down. System exchanges heat in or out to keep the temperature constant. And as a result, we have constant temperature and constant pressure conditions. Now my shaft work is again going to be defined by the constraints that I put on this system. Again, let's write the energy balance, du over dt, is equal to Q. Now I have heat exchange, shaft work, and I have surface boundary movement. Okay? So this combined with the entropy balance, the same term prevails here. Q is T ds over dt. I'm going to substitute that Q minus T ds over dt plus P dv over dt is my shaft work. Again, temperature is constant, this enters into the derivative. Pressure is constant, this enters into the derivative. So I collect them under 1d over dt term. We have u minus ts plus pv is equal to shaft work. And this is the Gibbs free energy. All right. So we finalize this by carrying out the integral and to show that the shaft work without a dot is equal to delta G. Now this is a very fundamental issue in terms of these 4 different forms of energy: internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. Now those 4 different constraints correspond to volume and entropy, pressure and entropy, temperature and volume, or volume and temperature, and pressure and temperature lead to U, H, A, and G as the defining energies for our systems if we are doing a shaft work for exchange of energy with the environment. Now, seeing this picture from this angle is going to be hopefully useful in addressing the problems that we are going to attempt from this point on, because from this point on, we are not going to limit ourselves to ideal gases only. We are going to look at the molecular interactions in the real gases and how they exchange energies. Those molecules, how do they exchange energies? But here, we have also set the thermodynamic landscape. We have 4 independent variables. Those 4 independent variables are temperature, entropy, pressure, and volume. And perhaps you have noticed while solving this problem, one or the other of these 2 and one or the other of these 2 was present as a constraint. All right? So now we see that those 2 can be represented in terms of the other, and these 2 can be represented in terms of the other. Okay? When we keep the pressure constant, we need to allow volume to change. If we keep the volume constant, we have to allow the pressure to change. If you're going to keep the temperature constant, we have to allow the entropy to change. If you're going to keep the entropy constant, we have to allow the temperature to change, one or the other. All right? On the other hand, we have 4 different forms of energy: internal energy. This is the energy stored within the molecules, internal to the molecules. Vibrational, rotational, and translational degrees of freedom. And if you are breaking bonds or making bonds, it's the chemical bond energy as well. Here, enthalpy is U plus PV. All right? This is the energy stored in the molecules, and also we have to allow some energy to be exchanged with the environment because our piston is doing work against the environment or is absorbing energy from the environment. All right? That is why we have the enthalpy. Helmholtz free energy is U minus Ts. All right? And this is the internal energy, the same energy in the molecules, minus the energy needed to keep the system temperature constant. We have to account for the energy that we have to give away to keep the system temperature constant. Hence, we free the system, free the energy from the energy exchange to keep the system temperature constant. And of course, Gibbs free energy is going to be U minus Ts plus PV. Gibbs free energy is A plus PV, or Gibbs free energy is H minus Ts. And Gibbs free energy accounts for the internal energy of the molecules. It accounts for the work that we have to do against the environment, or the environment does onto the system. And it has to account for the energy that we have to exchange with the environment in order to keep the temperature constant. All right? So these four different forms of energies are going to take us to a new dimension, to a new domain, where now we can do some detailed mathematics and then use these detailed mathematics to estimate the properties of the real fluids within the context of this lecture. Now we are going to release the constraints on the systems, and we are going to let the systems evolve to equilibrium, and let's see what happens. Now, in the first part of the process, we had a system constraint through volume and entropy, that we kept entropy constant and volume constant, and internal energy was equal to the shaft work done on the system, or shaft work was equal to the the change only in the internal energy of this gas confined in the system. Now I'm going to remove the constraints, and I will let the system evolve to its natural equilibrium. And I'm curious how the system is going to evolve to the equilibrium, and what are the process parameters that are going to change during that evolution towards equilibrium. Remember, I'm going to remove the constraints. I'm going to remove the shaft work now. And I'm going to remove the condition of insulation, adiabatic domain. So my constraints are going to be relaxed. Now let's see. I will stop the shaft work. And I will now let me keep, for the sake of discussion, let me keep the condition that the system is under adiabatic constraints. I will stop the shaft work, and my system is going to evolve to a state where du over dt is equal to 0 and ds over dt is equal to 0. Okay? This ds over dt is equal to 0 is coming due to the conditions that we have set in the beginning, but let's translate this differential concepts into concepts of equilibrium. All right? At equilibrium, the time rate of change of the variables were 0, or equilibrium was time independence under natural flows. So I removed the only unnatural component in this process was the impeller. I stopped the impeller. My system evolves. The moment I stop the impeller, my system evolves to a state where U is independent of time and S is independent of time. Of course, the condition of derivatives being equal to 0 also refer to maxima or minima. All right? In other words, these two terms may refer to extrema in those energies. All right? So when we remove the natural forces from system, when we remove the external forces or external constraints from a system, the natural direction that the system takes is to assume a minimum energy. A minimum energy. If I drop the pen, it will assume a minimum energy. All right? So this constraint at the same time refers to a system evolving into a minimum internal energy. But on the other hand, the system will evolve to a maximum in the entropy. The natural direction of the processes in terms of entropy is to evolve to a maximum entropy. This maximum in entropy comes from our second law statement. Entropy of the universe is always increasing. Entropy of the universe is always increasing, or S generated is equal to, is greater than or equal to 0. So in this first system, our internal energy was minimized and entropy is maximized. Now let's go to the second system. Remember, we had a system where our piston and cylinder assembly was under constant pressure and constant entropy constraint. All right, we had an impeller. Our system had d over dt. dH over dt is equal to shaft work. And we stop the shaft work. We let the system evolve under natural forces. All right. As a result, dH over dt is going to be 0. In other words, we're going to have this system at constant pressure and entropy will evolve to an H minimum state and S maximum state. All right? Our system is going to evolve to a minimum enthalpy and maximum entropy state. The system that is going to have the constraints of constant temperature and constant volume, if you remember, it was a dA over dt to be equal to shaft work system. All right. Now we were imposing externally two different energy interactions. One was shaft work exchange, the other was heat exchange. All right? Now we are going to remove both of them. We are going to let the system evolve to a state where dA over dt to be equal to 0. We are going to minimize A the system is going to evolve to a minimum Helmholtz free energy, but it is not going to be very easy to make any remark about the entropy at this level. We will come back to that. The final system had a pressure and temperature constraint. We lift the external forces. We remove the external interactions, which is the shaft work and heat exchange. Before we did that, it was dg over dt to be equal to shaft work. And this system is going to evolve into, after those constraints are lifted, this system is going to evolve into dg over dt to be equal to 0 state, or we are going to minimize the Gibbs free energy at equilibrium. As a result, let's summarize. If I evolve a system at constant volume and entropy, the system will achieve a minimum internal energy. If I evolve a system at constant pressure and entropy, it will evolve to a minimum enthalpy. If I evolve a system at constant temperature and volume, it will evolve to a minimum Helmholtz free energy. If I evolve a system at constant pressure and temperature, it will evolve to Gibbs free energy. All right? So those are the constraints in relationship to the energies, constraints in relationship to the energies. And of course, there will be one more step that will take us to the whole new definition of those energies. Now let us consider a gas in a domain. The different color is going to reflect the change of the conceptual approach a little bit. We are going to have a domain with the boundaries, closed system, the system may expand or contract, and the system may exchange heat with the surroundings, but no other interactions. All right? The system may expand or contract, so just consider that as a gas confined in a balloon, or the gas confined in your lungs for the moment that they remain there. All right? The domain is closed, and there is no shaft work exchange. Heat exchange is permitted, and the system can expand and contract. The energy balance reduces. The energy balance reduces for this system as du over dt is equal to q minus p dv over dt. And as we were deriving the equations, we learned now to substitute q in terms of the entropy as the state variable. And now our equation evolves to du over dt is equal to t ds over dt minus p dV over dt. All right, this is going to be the start of the new approach that we're going to follow from this point on. Internal energy change here in this closed domain where no shaft work is done. Internal energy change is a function of entropy and volume. Internal energy is a function of entropy and volume. We can drop dTs from these equations and revert back to our yellow colored pen to have the final form of the equation. du is equal to T ds minus P dV. Here we have entropy and volume, where we had entropy and volume. And if the connection is not clear, it will be in a short while. Now let's do the same here. We have a closed system where there is no shaft work, but we have this gas. Internal energy is now T ds minus P dV. We are going to write the counterparts of these expressions from the definitions of enthalpy, Helmholtz free energy, and Gibbs free energy. Now let's write the definition of the enthalpy. dH over dt is equal to d over dt U plus PV this is going to be du over dt plus P dV over dt plus V dP over dt. Oops. I'm going to bring du over dt from here as T ds over dt minus P dV over dt. Or I can just drop dt's from this equation and just bring this differential form. dH is equal to T ds minus P dV plus P dV plus V dP, or dH is equal to T ds plus V dP. Enthalpy is a function of entropy and pressure. Enthalpy is a function of entropy and pressure. Okay. Let me derive the equivalence of these expressions for the Helmholtz and Gibbs free energies. Also, remember the A over dt. A was defined as U minus Ts So this is going to be du over dt minus t ds over dt minus s dt over dt. These t's were eliminated from the analysis. We have dA is equal to du. Du is equal to T ds minus P dV. T ds minus P dV minus T ds minus S dt. Or these two terms cancel, and dA is equal to minus S dt minus P dV. Helmholtz free energy is a function of temperature and volume. Helmholtz free energy is a function of temperature and volume. Let's get our Gibbs free energy definition incorporated into the analysis. U minus Ts plus PV. We can take either the direction from enthalpy or from Helmholtz free energy, or we can just start from the internal energy, which I will do, is going to be du. Now I will skip the dt terms. dg is equal to du minus tds minus sdt plus pdv minus plus v dp. I will bring du as tds minus pdv minus tds minus sdt plus pdv plus vdp. So we now cancel these to have dg to be equal to minus sdt plus v dp. G is a function of temperature and pressure. So now these constraints that allowed us to determine the shaft work, or these constraints that allowed us to obtain what is the minimum energy, are actually the independent variables that we use in the thermodynamic landscape. The independent variables that we use in the thermodynamic landscape along with their corresponding energies. So I'm going to write, maybe in a different color, to emphasize here that internal energy is a function of entropy and volume. Enthalpy is a function of entropy and pressure. Those are my independent variables. If my independent variables are entropy and pressure, the energy that I'm dealing with is enthalpy. Why? Because those constraints evolve into this balance equation, evolves into minimization of that energy under natural forces. Helmholtz free energy is a function of temperature and volume, and Gibbs free energy is a function of temperature and pressure. All right. And of course, let me carry this one along with the overall domain. So these expressions are going to be very useful to us when we are navigating in the energy landscape of the thermodynamics.